In this lecture, we'll discuss the concept of collections in an object-relational database management system. Because we're using Oracle database, we'll discuss the two collection types that Oracle supports, the nested table and the V-array. A collection is a group of elements that are all of the same data type. The collections are used to provide a way to model and subsequently implement a relationship that might have a cardinality of one to many. As we had mentioned, Oracle supports two types of collections. There's a nested table. This can have any number of unordered elements. We'll talk about this in more detail in just a moment. Then there's a V-array, what we refer to as a variable size array. When a V-array type is defined, we impose an upper limit or an upper bound on its capacity, so it has a maximum number of ordered elements. Collections can have only one dimension. However, to achieve a notion of a multidimensional characteristic or property, collections can be nested within other collections. This means that a collection can have as its elements other collections. There are restrictions on the use and behavior of collection types. A V-array cannot contain large objects, or what we call lobs. It can contain elements of a user-defined type, but these elements cannot contain a large object attribute. So large objects are out if you're using a V-array. A nested table cannot contain certain types of large objects. It cannot contain an N-clob, which is a national language character large object, but it can contain a clob, a character large object, and a blob, a binary large object. Because V-arrays and nested tables are implemented as data types within the system, they will have a system-generated constructor, or as Oracle calls it, a constructor method, that is defined for these types in order to create instances of these collection types. V-arrays and nested table types do not have explicitly defined methods. However, there is a set of system-supplied methods that we will examine as we discuss these collection types in a bit more detail. Note that if the elements of a user-defined type has methods, then these methods can be used to manipulate the collection elements. But again, the V-array has no user-defined methods. Comparison of collections is not directly supported. We'll talk a bit about how to achieve this down the road. Now, we mentioned there were two types. How do you decide which type is appropriate for a particular implementation? The decision to use nested tables, or V-arrays, can be determined by understanding the situations that favor one approach versus the other. Let's first consider the V-array. Let's use a V-array when we need to store only a fixed number of items. Remember, we said that when a V-array is declared, we define an upper limit on its capacity. We can use a V-array when we need to loop through or iterate through the elements in an order, because remember, the elements in the V-array have an order imposed on them. We can also use a V-array when we want to retrieve and manipulate the entire collection as a value. We'll discuss this and present an example as we go along. Now, turning to the nested table. We'll use a nested table when we need to run efficient queries on a collection, because a nested table can be queried in a way that's similar to how we would query a traditional table. We use a nested table when we need to handle an arbitrary number of elements. There's no upper bound on a nested table as there is on a V-array. We can also use a nested table when we want to do mass insert, update, or delete operations against the data contained within the table. Nested tables differ from V-arrays in a few different ways. V-arrays have a maximum size. Remember that nested tables do not. V-arrays are always dense. Nested tables can be sparse. And what that means is the V-arrays, the elements are always contiguous. There are no gaps. Whereas with a nested table, we can have some gaps between the elements. And again, we'll discuss the internal storage structure in just a bit. So this means you can delete individual elements from a nested table. This is what contributes to it having that sparse characteristic. A V-array has data that may be stored in line. If the V-array contains a relatively small quantity of data, it's embedded in line within the table structure. However, as it grows and exceeds a certain capacity, then it will be stored out of line. On the other hand, the data for a nested table will always be stored out of line in what's called a store table. So the V-array then is stored as kind of a dense or opaque object. When stored in the database, V-arrays retain their ordering and the subscripts, but nested tables do not. Now keep in mind that a collection type is a user-defined type itself. We have to create a collection type before we can create collection objects based on that type. So just as with object types that we've discussed in some detail, we could store the object type in the database, or we could have kind of temporary or transient objects that are working storage variables, say in a PL/SQL program. The same is true for collection types. The objects of these types can be made persistent and stored in the database, or they could be temporary or transient in nature, basically the data type of a working storage variable in some application that we might be working on. A nested table can be thought of as a one-column database table. See, the table type for this nested table will be the data type of a column in some other table. The elements may be built-in types or user-defined types. The rows are stored in no particular order. This is characteristic of any relational table. Hence, a nested table is like another relational table, but it is nested or embedded within the column of another table. Rows that are retrieved into a PL/SQL variable are given consecutive subscripts beginning with an index or subscript value of 1. Note that the subscripts cannot be 0, nor can they be negative. When used in the database, nested table data will be stored in a single table associated with the enclosing relational or object table for which the nested table is a column or attribute. This is what we had referred to previously as the store table. Let's consider a programming language array and compare and contrast that with a nested table. First, a nested table is unbounded. We don't have a limit on its capacity. An array is dense. It has consecutive subscripts. Initially, a nested table is dense, but as we had noted previously, it could become sparse as a result of deletion operations. So in our figure here, we give the idea of the array being fixed in size, having an upper bound, but notice it's also dense. Every cell is identified. and in this case populated with an integer value. When we have a nested table using the same data type, a nested table of integer, we draw it here as having a certain capacity, but we note that this is unbounded. We can go beyond what we've shown here. Currently, we're showing 8 slots, but this can exceed that, whereas the array has reached its upper limit, predefined as having a capacity of 8 slots. But what we want to point out from the figure is the sparse nature of the nested table. Here, the nested table has only 5 of the slots currently populated. These other slots have not been assigned values. This is not the same as having a slot that has been allocated and then emptied. The slot actually has not been initialized. So how do we define a nested table? Well, a nested table first has to have a type. So we create the type. So we say create or replace the type, give it a name, and say this is a table of, and then we specify what the content will be. This could be a table of integer, or it could be a table of some object type, but it will be a table of something, a collection of some data type. And what we've done here is not create the table itself. We've only announced what the table type, the nested table type, will consist of. We've created that type. The data of a nested table is stored outside of the containing table in the storage table or the store table. We've made that point a few times already. The name of the storage table is specified when the containing table is created. This is the table that will house the nested table. So we will then say create table, and here's our, say, relational table. We define a bunch of columns, and one of the columns is designated as having the data type of the nested table, the type name. In addition, we specify one more clause when creating this table. We define the nested table's storage table. Store this as, and we give a name to this table. We identify the column within this relational table that will hold the nested table, and then say, store this as some table. We can do much more with this clause. We can define physical storage characteristics of this. It is possible that we could have the containing table stored in one table space and the nested table stored elsewhere. So we can control physical storage characteristics of that. But my goal here is to simply convey the idea of the basics of how to create the containing table and the nested table. The storage table is a single table that holds all of the nested table rows within the containing table. That's a very important point that we'll stress as we go through our examination of nested tables in some detail. The rows associated with a single nested table instance, that is the nested table column for a single row in a containing table, these rows are identified by a special hidden column called nested table ID. The creator of the table can specify how the data of the nested table will be stored within the database. We can use a conventional relational table as our nested table, or we could use something called an IOT, an indexed organized table. The nested table can be specified as having its own primary key, effectively independent of the primary key for the containing table. Let's look at a simple example. First, we're going to create a type. And this type is an object type, but this will serve as the data type or base type for the elements in our nested table collection type. So we're going to create the type called class, and we spell it with a K. We don't want it to conflict with our academic table, which has one of the tables has the name of class, CLASS. And again, if you're working in IT or you're a programmer, you tend to have not very good spelling qualities or characteristics, I guess, anyway. So spelling it with a K probably doesn't get you too disturbed. But the reason we're doing that is to keep it distinct from a class table that we have in our academic database. Once we create this class, we can then go ahead and create the nested table type. The nested table type will be called classes, again spelled with a K, and it is a table of these class object types. We can use the SQL+ command and describe classes, and we find out, sure enough, classes is a table of class. So we've seen this idea pretty much already when we created an object table. However, what we want to note here is we're not creating an object table. We're creating a type of objects. So classes, in this case, is a nested table type. It doesn't allocate storage. It's just metadata at this point that describes the structure. In our examination of collections thus far, we have defined or created two types, an object type and a nested table type, which is one type or one form of a collection. We remind you that collection types don't have user-defined methods, but they also do not have attributes. If we examine the metadata about user types, the type name is class for our object type and classes for our collection, which is actually a nested table or nested table type. Note that for the attributes, we see 0 attributes for classes, but we also see 0 methods. Recall that we're emphasizing there are no user-defined methods, but there are methods that are created by the system, which are predefined or pre-built functions or procedures that can be used to operate on collection objects. Those are not reflected here in the method count. Let's create a table with a column that is based on this nested table type. So here we create the student table. We have student number as the primary key of this relational table. Student name, and then the third column, we call it schedule, but this will be an instance of the class's nested table type. When we specify that a column is a nested table, we have to then provide information about the storage of this object, the store table. In this example, we say that nested table is schedule, the name of the column, and that we are to store as a table named nested student schedule. That's the nested table. When we go and describe student, the name of the table we just created, we see the following information. The structure of this store table can actually be examined. We can say describe nested student schedule. Remember, that's our store table. However, we cannot directly access this table. We can't run a query such as select asterisk from nested student schedule. This table is only accessible from within the containing or the parent table. So we first have to grab hold of a row within that table, in this case within the student table, and then we can kind of drill down and examine the nested student schedule for that particular row. But again, the parent row must provide a context in order to access the content of the nested table. Because the nested table is not a conventional relational table, no metadata exists for it in user tables. So when we say, what tables do I have? By running a query of select table name from user tables, we see only an indication of the student table. The nested table is not returned here. Information is, however, available about the nested table by looking at the metadata from a different angle. If we examine user all tables, then we say, show me the tables. There happen to be a couple of additional columns here. There is a column to indicate whether the table that you're viewing is a nested table, and also the data type of that table. It's a collection of what? So here, the output of this query reveals that student is not a nested table. That makes sense. We know it's a regular relational table. But nested student schedule, our nested table, is displayed when we query user all tables, and it's shown or confirmed as being nested, and its composition is a collection of class objects. We can examine another data dictionary view called user nested tables. This contains information about the nested table and its relationship to the containing or parent table. In this query, we are identifying the name of the nested table, but also the parent table which contains it, and also within that table, the column. So we see that classes is contained within a table called student, specifically within a column called schedule. This is the description of user nested tables. You can take a look at it. We've already examined some of it. I'm going to move ahead. Another more general metadata source is what's called user call types, which contains information about our collections. At the moment, the only collection we've worked with is a nested table. So when we query user call types, we see that we have this table type called classes, and it is a nested table. The collection type is table, and it is a collection of class objects. And here you find the description of the columns within user call types. The collection objects are dependent upon the table objects in which they've been embedded. We can find information about this dependency or this association by querying a little bit more metadata, user dependencies. So here we find information about the classes type, referencing the class type, and nested student schedule, which is our nested table, a collection table, is referencing the class type. Remember, the table that we have is a nested table of class or class objects. And then furthermore, classes is within student. So the information is well documented and well recorded within the system regarding relationships and associations of our collections and the objects in which they've been embedded. Now that we've taken a look at how a nested table can be created within a relational table and examined some of the metadata, let's now consider how to populate that nested table. What we want to do is insert a row into the student table, and recall that the third column is our collection column. This is where the nested table resides. So it'll be necessary to invoke the constructor for this nested table type. In addition, this nested table happens to be a collection of objects, so we'll also have to invoke the object types constructor. So what we're doing here is inserting into the third column the result of invoking the classes nested table type constructor. But within that, for each class that the student has registered, what we'll do is invoke the class object type constructor. So Mo has registered for a single class, C1101. Larry has registered for C1101 and also C2203. With the data now in the table, we can perform a simple query to retrieve the content of the table. So we retrieve the scalar value for the student number to identify the student, and we also retrieve the class information that pertains to the schedule for that student. When we do this, we get something that may not be usable by application software, depending upon whether the application software can work with a collection in its entirety. Here, I've presented the output in a nicely formatted manner. However, when you run the query and you have a situation where you have our student Larry, who is registered for multiple classes, that is, there are multiple elements within the nested table, it wouldn't be presented as nicely as I've shown it here. It would simply run together and wrap around multiple lines when we display it on the screen. That's because the entire object, in this case, the entire nested table object, is returned to the application. What we need is some way to remove the individual elements. This is referred to as unnesting the table. We accomplish this by using something called a table expression, or the table operator. The table operator will accept as input the collection and effectively flatten it. So the collection will be flattened or unnesting, giving us the individual elements, which can then be accessed by most applications. The way we accomplish this is by extracting the collection content and then rendering it as a table and joining it with the table from which we extracted the data. So here we're selecting from the student table the schedule. Notice the use of the correlation variables. Student is associated with this table alias or correlation variable of S, which is used to qualify the names of the columns within the student table. We then use that S to qualify the collection schedule. That s.schedule is what is passed as input to the table operator. Because the table operator effectively produces a table, we give that a correlation variable as well, so that we can qualify the attributes of this table. So here we're calling the result of the table operator k. And what we're doing is simply saying select k.asterisk. Give me all of the columns from this unnested or flattened table. The result of this unnesting would be a single row for Mo, because he registered for a single class, but 2 rows for Larry, because Larry has registered for 2 classes. The nested table contained 2 rows. Each of those rows is joined with or concatenated with the information about the student number of 200 and the student name of Larry. We make the comment here that rows of the nested table are effectively duplicates when we consider only the content of the nested table. That is, when we examine what's in the nested table without providing the context of the parent row. So, for example, what we look at here is that if we examine the first 2 rows in this output, the row for Mo and the first row for Larry, and consider only those columns taken from the nested table, there are duplicate rows. So if we were to run the query to extract just the information from the nested table, selecting k.asterisk from student joined with the table expression result for passing schedule, we would retrieve everything except the student number and student name shown in the result here. And those first two rows would be duplicates. That's fine because it makes sense that when we access the information for a nested table or a collection in general, it only applies to the row in which it's been nested or embedded. So it's not likely that we would look at the table expression as we're showing in this second query. We'll take a closer look at this issue in just a little bit, and then we'll look at how to introduce integrity in the form of a primary key associated with the nested table. A table expression has its own table alias, separate or distinct from the alias of the containing or parent table. This table alias can appear in the select list to qualify columns that were generated by the table expression. The table expression can use the table alias of any table that appears to the left of this expression in a from clause. This is referred to as left correlation. In fact, it's a requirement that the containing or parent table appear to the left of the table expression. If we attempt to put the parent table, such as student, after, to the right of, the table expression, we generate an error because we violated the principle of left correlation. A table expression can also contain a subquery that involves a collection. There are restrictions on using a subquery with a table expression. The subquery must return a collection type, because the object of this collection type becomes the argument to the table operator. The subquery select list must contain exactly one item, and the subquery must return only a single collection. That is, it cannot return collections for multiple rows. So the subquery select P from E succeeds in a table expression only if table E contains just a single row. If the table contains more than one row, the subquery produces an error. Let's look at an example and we'll see how this works. Here the subquery is selecting the schedule column from the student table. Student is the parent or containing table, and schedule is the column that contains the nested table collection. Notice the predicate in the subquery. It identifies exactly one row, the row where student number is equal to 200. So for that single row, we are returning the schedule, the collection, for that student and that student only. That collection becomes the argument to the table expression, and then we select all of the columns or attributes from that expression. When unnesting a collection, there is a join operation that is performed between the parent or containing table and the table produced through the table operator. This is an inner join. What does that mean? It means for each row within the parent table, we will join it with the table result for the collection for that row. But what happens if a collection is null for one of these rows? The containing row then would not be preserved because it's an inner join. Therefore, we must use an outer join. So the outer join operator that Oracle has is the plus sign enclosed within parentheses. This is used to indicate that the dependent join should be null augmented. Right? We have a null extended row. If the collection for a containing row is null or empty, the containing row then will be preserved but have null values for the collection. Let's add an additional row to the student table. Previously, we had 2 rows where we had Mo and Larry. Each of these individuals had registered for at least one class. By inserting a row for Curly and using null for the collection, we're indicating semantically that Curly has not registered for any classes. The implication here is when we use the table expression and join that with the parent or containing table, because it's an inner join, Curly will not be reflected in the output because the table expression produces a null value. There's nothing to match. By making this an outer join, as illustrated in the bottom half of this example, we see that the row for Curly is preserved, even though Curly currently has not registered for any classes. Getting back to the point we were talking about earlier with respect to, say, the integrity of the nested table and duplicates, we can create a nested table that has a primary key. So working with our example, we first remove the existing version of student with the drop statement, and we create it again. This time, notice that when we specify the nested student schedule as the storer table, we include the primary key constraint, saying CNO and SEC will constitute the primary key, the unique identifier. It's possible to assign a name to the constraint, and that's what we're showing down below. We're specifying that this primary key constraint defined over the nested table will be called PKNSS. And again, it will consist of course number and section number. If we fail to give the constraint a name, the system will generate a name such as SYS_C003460. It will make up some number based upon a sequence. So it's better to give a name to the constraint. So we demonstrate both options here. Constraints on nested tables would also be recorded with the metadata for constraints for our traditional relational tables. So if we examine user constraints, we see this constraint called PKNSS as a primary key type of constraint, and the table over which it applies is the table called nested student schedule. If we examine user constraints together with user cons columns, we can obtain the names of the columns that apply to the constraint. So we supply the name of PKNSS as the constraint name and form the join of these two data dictionary views. And what we see is the combination of CNO first, followed by SEC, defines the composite primary key for this particular nested table. We note that a single storage table holds all the nested data for its parent table. So if the nested table is defined with a primary key, this will impose a constraint on what's going to be placed or what can be placed within this nested store table, regardless of the association with the parent row within the constraining table. So if we define this table, the nested table, as having a primary key, and we insert this first row for Mo, that will be successful. The attempt to insert the second row for Larry raises a problem. Note that Mo and Larry have both registered for C1101. It turns out that we will violate the uniqueness constraint that we define over the nested storage table if we define course number and section number as the composite primary key. And sure enough, the system throws that exception here. Now, nested tables can have primary key constraints. They can have not null and other types of check constraints, and they can also have unique constraints. Referential constraints, however, are not permitted on columns of a nested table. The column called CIN-STR-FNO identifies the faculty member who teaches the class. Normally, we would want this defined as a foreign key to maintain referential integrity to ensure that we have a valid faculty member associated for instructional purposes with the class. So this column, because of the inability to define a referential constraint, cannot be defined as a foreign key. The syntax for defining a nested table also allows the specification of default values for a column. There's a special hidden column that we briefly mentioned earlier called nested table ID. This column can be used in conjunction with actual exposed attributes or columns of the nested store table. We can then use this to define a composite primary key. So in this version of the student table, we're saying that the primary key actually consists of 3 columns in total: the nested table ID hidden column and the 2 visible columns of CNO and SEC. The metadata is shown here when we query information about nested student schedule and information about the constraints. By including this 3rd column, this hidden column, this will allow us to have 2 or more students who register for the same class without presenting a conflict violating uniqueness. The other collection type is called a V-array. With a V-array, we can manipulate the collection as a whole. If we're working with the V-array from the database, we may bring it into working storage, into a variable defined as being of that type of V-array, and then we can work with that object within the application program. We also can reference individual objects, and this is done by using a subscript notation. In fact, the elements are ordered according to a subscript or index type of value. The number of elements in an array determines what we call the size of the array. When a V-array is created, we specify an upper bound, or the maximum size. Just as with the nested table type, V-array is also a type. We can create instances of the V-array, but the type must already exist. We accomplish this by using the create type statement. We give a name to the type, and we say that it is a V-array and specify that limit or that upper bound. Then we indicate the composition, what type of element will be stored within the array. So the limit is an integer of 0 or greater, indicating the maximum number of elements allowed in the array. The data type could be a built-in data type, a scalar data type. It could be a ref, indicating it's a reference to some object somewhere. We could have a collection of these references. Or it could be an object type, a user-defined type. Our example begins again by creating a data type that will be used as the data type for the elements of the collection. Here we're creating an object that we call class. Note that we're reverting back to spelling class with a C. This is to be able to differentiate or distinguish our V-array from our nested table, which we spelled with a K. We then create the type, the V-array type. We say create type, we call it classes, and we say that it will be a V-array of up to 5 instances of a class object. We can create a table that uses the VArray as a collection type. Here we're creating the course table, and observe the column called sections. Sections is a VArray. It's defined as this classes type. So within each course row that we insert within this table, we can schedule up to 5 sections or classes for the course. Remember that by embedding the collection within this table, the course table serves as the parent table. It will then be necessary to access the course table to obtain the section or schedule information for classes that are being offered for that course. The user VArrays dictionary view describes the VArrays within the schema of the current user. We've created the course table, and the course table serves as the parent table for one of our VArrays. The table column that will contain the VArray collection is called sections, and it consists of a VArray of classes. It's defined as the classes VArray type. User VArrays consist of the columns that we've identified here. If we examine user collection types, user call types, we can find out more information about the VArray. Remember, we visited this same data dictionary view when we were examining some of the metadata associated with the nested table type. The information of interest to us for a VArray is a bit different. We have the name, which is classes. The collection type in this case is a varying array rather than a nested table. Upper bound is now applicable. This was not applicable with the table. And the element type name is class. We have class objects. There's also metadata associated with the dependencies of the VArray. This is the same view that we examined when we looked at dependencies for the nested table type. The column that we've designated as a VArray can be populated by invoking the constructor for our VArray type. If the VArray contains other user-defined types, the constructor for those types must also be invoked. This was the case when we examined the nested table. It will also apply here for our example of VArray, because the sections column is of type classes, the VArray type, but classes is a collection of class objects. So we'll need to invoke both the classes constructor and the class constructor. We're inserting 2 rows into the course table and including the associated class information in the sections column. So we invoke the classes constructor, and for each offered section, we are invoking the class constructor to define the class objects. We can retrieve data from the VArray by, again, unnesting the collection elements using the table operator. Using the subquery approach, we select from the course table, which we call C.sections. And we again are retrieving a single row. We're retrieving the section information or the class information for course number C11. And the query returns the appropriate information. We then look for C22. Oracle supports DML operations on nested table columns, including piecewise updates. Piecewise updates include inserting new elements into the collection, deleting elements from the collection, or updating elements of the collection. Piecewise updates on V-array columns, however, are not supported. V-array columns can be inserted into or updated as an atomic unit. Remember, we said that this data type is kind of opaque, so we can retrieve the collection into working storage of our application, manipulate it effectively within that application, and then take the modified version and overlay or replace the version in the table that we retrieved the collection from. So we have introduced two types of collections, the nested table type and the V-array type. There are some similarities in terms of what can be stored, but how we work with the data is different. And capabilities of the two collections, bounded and unbounded, for example, are different. Through our examples, we have shown that a collection provides a way of representing the many values in a one-to-many relationship. These values are logically contained within the row representing the one in that same relationship. The objective of this video was to give you an overview of the collection types supported in an object-relational database, and specifically those supported within the Oracle database. We wanted to give you an appreciation for how these things work in terms of defining them and what their capabilities are. Note that in our examples, we focused primarily on SQL. SQL is used to create these objects, but when working with the individual elements, more than likely we're going to be doing that kind of manipulation from within an application such as a PL/SQL program. This is because you cannot update or delete individual elements of a V-array directly with SQL. It's necessary to select the V-array from the table, change it in PL/SQL, then update the table to include the new V-array. This update will replace the version of the V-array that was brought into the PL/SQL program. Note that it's also possible to work with nested tables in this same way. However, nested tables allow piecewise updates and deletes, so we can accomplish such operations with SQL alone.